Hey there, and welcome. This is the second part of our series going over the fundamentals of computing. If you haven't yet, watch my first video on binary and hex using the link above. For this series, I recommend grabbing a pencil and paper for notes and diagrams, or if you use any note-taking software, to use that. Logic gates. You may not have heard of these, but they are an essential part of computing, making up the basics of everything in your computer, from your processor to your memory. So what are they all about? What do they do? And how? Logic gates make up logic circuits. For ease, we can think of them as valves. Valves that control data flow. There are 7 main logic gates, plus a buffer gate. Each gate has its own symbol and way of handling data. Let's go over each one now. The AND gate is first up. As you can see, it is D-shaped. You can see from the diagram we have inputs, 2 of them, an output and a truth table. The truth table uses binary to show all possible states of a logic circuit, helping us clearly see how the gate behaves under every possible input combination. If you can recall from the first video, we can consider 0 an off state and 1 an on state. Back to the diagram. The AND gate controls data flow by only allowing an output if all its inputs are in the on state, hence why it's called an AND gate. Let's visualize this and connect it to some rails. So, as we can see in the truth table, if both input A and input B are off, there's no output. If input A is on and input B is off, there's no output. And the same again if input A is off and input B is on. It's only when both input A and input B are on that we can get an output. Next up we have the OR gate. As you can see, it is a crescent-shaped gate. This particular example has 2 inputs and 1 output, and we have our truth table. The OR gate controls data flow by only allowing an output if at least 1 input is in the on state. So, it can be input A, input B, or both. Let's see this. As we can see in the truth table, if both input A and input B are in the off state, we have no output. If just input A is put into the on state, we have output. We see the same if just input B is put into the on state. And we also get output when they are both in the on state. These are our main 2 gates. Everything from now on will be a variation of them. But before we delve into them, let's look at the NOT gate. The NOT gate is special. It typically only has 1 output and 1 input. This gate naturally always has an output in the on state. Unless we give it an input, then its output turns off. Think of it as reversing our input. We denote the NOT part of a gate, the piece that reverses the signal, as the small circle here. If any gate has this, you'll be able to tell that it also reverses the input given. Let's see quickly. As we can see in the truth table, the input A is off, or 0, but our output is on, or 1. Now turning on input A, making it 1, we can see we have no output, or an output of 0. Easy. Now let's apply this knowledge to our next 2 gates. First up, we have the NAND gate. The NAND gate, or NOT AND gate, functions similarly to the AND gate, though the output is only in an off state when all inputs are in an on state. Let's go through it. As shown by the truth table, when both input A and input B are off, we have an output. Now, when just input A is on and input B is off, we still have an output. The same happens when input A is off and input B is on. But when both input A and input B are on, we have no output. Moving on, we have the NOR gate. Functionally similar to the OR gate, we have the NOR gate, or the NOT OR gate. This gate only outputs when no inputs are in an on state. Let's see this. So when input A and input B are in an off state, we have an output. But if we turn input A into an on state, we get no output. The same for if we just turn on input B and both inputs, as seen in the truth table. Now we've gone over the NOT variants, let's look at the exclusive variants. These variants are only of the OR gate. Here we have the XOR, or sometimes seen as the EOR gate. It's the same thing. It's an exclusive OR gate. We can tell it's an exclusive gate by the denotation of this curved line just before the gate on the input side. The XOR gate is the same as a normal OR gate, but it only accepts exclusively one input or the other. Let's see this. So, with both inputs off, we have no output, just like the OR gate. We see the same behaviour as the OR gate when we have either input A or input B in the on state, giving us an output. But when we have both input A and input B on, we then lose output. Now let's look at the XNOR gate or the ENOR gate. This is the exclusive NOT OR gate, and it is almost identical to the NOR gate. Looking at the truth table, when we have both inputs A and B in the off state, or 0, we have an output of 1. When either A or B is in the on state, or 1, we have no output, or 0. If we have both inputs in the on state, we have output. Like the XOR gate, it exclusively accepts only one input to get the output to go into the off state, or 0. That is the main 7 logic gates. Now let's look at a bonus gate, the buffer gate. This gate is not used for much else other than signal amplification. As we can see, this gate is truly a simple gate. While it looks like a NOT gate, it does not invert the signal. If the input is in the off state, the output is in the off state, and likewise, if the input is in the on state, the output is also in the on state. Now we've gone over the logic gates, let's see how and why they are used and important. Let's go over logic circuits. Logic circuits use logic gates like puzzle pieces to make a whole. In this section, we will look at some common logic circuits. So let's first take a look at the half adder. A half adder is a fundamental logic circuit that adds 2 single binary bits. It has 2 outputs, a sum for the result of the addition, and a carry if this sum exceeds 1 bit. As we can see, this simple circuit consists of an XOR gate and an AND gate. Let's go over how it works. We have our 2 inputs as usual, A and B, and we will call the output of the XOR gate the sum, and the output of the AND gate will be our carry. As mentioned earlier, this circuit will give us the addition of 1 bit. If it overflows to 2 bits, it will go to our carry. So let's see this in action. As we look at the truth table, if I give an input, in this case a bit, via the A rail, it will flow to both the XOR and AND gates. But only the XOR gate will activate. This gives us the answer in a single bit, the sum of 1. So our answer is 1. The same happens if I supply a single bit to just the B input. But now, when I give both inputs a bit each, the XOR, not allowing 2 inputs at the same time, closes, and the AND gate takes the input and opens, giving us a carry. This we can think of as a second place in a 2-bit number, giving us 2, which if you remember from our binary video is 10, which in decimal is 2. We can use the half adder to make a full adder. The full adder is functionally the same as the half adder, except with the inclusion of a carry in, as you can see. Let's step through the full adder and show the full process. If all inputs A, B and carry in are in the off state, the sum and the carry out outputs will be in the off state also. If I just give A bit and leave B and carry in the off state, we get a bit in the sum, and carry out stays in the off state. Same for if I supply just a bit to the B input, or the carry in input. When we supply 2 bits either to A and B, or A and carry in, or B and carry in, only carry out will get a bit. And finally, if I supply all inputs a bit, both sum and carry out will get an output. And as we know, 1, 1 is equal to 3, which is how many bits I gave it. Full adders can be strung together if you link the carry out to the carry in of a new one, allowing us to count in different bit ranges, like so. This is an 8-bit ripple adder. I will not be attempting the truth table for this, as it would be over 130,000 rows long. So what else can we use logic gates for? How about storage? This is an SR latch. Whilst it doesn't look as complex as an adder, this little circuit is capable of storing a bit and resetting it. This is how RAM works. In this example, there are 2 versions, but for now, all we need to know is that they do the same job in just a slightly different way. In these circuits, a singular bit is stored in the Q position, and a complementary but inverse bit is stored in the negative Q position. Let's go through the truth tables. For the active high SR latch, when both set and reset are in the off state, we have no change to the stored bit. This is known as the hold state. In the hold state, the SR latch simply stores the previously set bit, either a 1 or 0, effectively remembering it. When we activate the set position, it places a bit in the Q position, stored as a 1, and the inverse 0 in the negative Q position. When we activate the reset position, it resets the bit in the Q position back to a 0, and sets the inverse 1 in the negative Q position. Lastly, we have an invalid state, which is when both set and reset positions are activated. This should never happen. Now let's look at the active low SR latch. The hold state for this circuit is when both set and reset are deactivated. In this case, the active position is 0 and 1 is deactive. When the set position is activated, remember 0, the Q position holds the 1 bit, and the negative Q the inverse 0 bit. When reset is activated, again remember it would be a 0, the Q position is reset to a 0, and negative Q back to a 1. And if both the set and reset positions are active, we get the invalid position. So, we've seen how SR latches can store a bit of information, but in a real computer, operations don't just happen whenever inputs change. Everything needs to be perfectly synchronized. That's where flip-flops come in. Flip-flops are essentially an advanced type of latch that uses a special input called a clock signal. The flip-flop will only change its stored bit at a very specific moment, or edge of this clock signal. That's all we need to know right now, as we don't want to overcomplicate things. Using all we know about logic gates, we can build quite a lot of things, like this for example. This is a crude 4-bit adder with registers. Registers are temporary storage. We can set a number in the first register, another in the second register, and then the answer is in the third register. A very simplified example of what happens in the CPU's ALU. An ALU, or Arithmetic Logic Unit, is where the processor does all its arithmetic operations. But for now, that's all there is to know about logic gates. If you want to try and make circuits for yourself, a good website to try is circuitverse.org, where you can make and play with interactive logic circuits. But give it all a go, see how many logic circuits you can make and understand. If you're enjoying these videos, leave a like and don't forget to subscribe too. And if you have any questions, feel free to reach out to me directly at fluffies.bytes@gmail.com. I'd love to hear from you. Don't forget to join me in the next episode where we start looking into the basics of programming, tackling some universal concepts of programming. But for now, have fun and I'll see you in the next video.